Welcome. My student asked me about the inspiration and intuition behind DLITE theory, DLITE. And I would like to use this video to highlight a few things that motivated me to start this project and this process to discover this new information theory. So first, what is DLITE? DLITE stands for Discounted Least Information Theory of Entropy. And it has a very interesting set of theoretical properties, as well as very strong and competitive results in applications such as information retrieval, text mining. So I listed here are a couple of papers related to this discussion. One is the theoretical paper on DLITE, which outlines some of the key properties in the theory, and then the other is the application paper published in the Big Data Conference, which show very competitive result of DLITE in information retrieval experiments. Okay, so there is also a video presentation about this big data paper, so you can take a look, and I also lay out some theoretical foundation of this paper in the presentation there. Okay, so but in this video, which is going to be brief, I will highlight a few things that a gap in the existing theory and development, and just to show you why I wanted to find an alternative theory in DLITE to better support, the development of algorithms and scoring functions in related areas of study. Okay, so the first point I would like to highlight is that in information retrieval, in text mining, in natural language processing, when you have to deal with text data of human language, TFxIDF, okay, text term frequency times inverse document frequency is the most classic method, okay, to process data and to represent terms and words, and for scoring function, for the scoring and ranking function in information retrieval. So this is the most classic method, and the a variant of TFxIDF is BM25. But basically, either TFxIDF or BM25 had this common component of IDF, which is inverse document frequency. And on the theoretical level, IDF can be derived from information theory, such as KL Divergence and cross entropy. So, by the way, cross entropy is a very popular method today as a loss function in lots of AI, deep learning, and GPT training. Okay, so this is it's a widely used method. Okay, but IDF, inverse document frequency, can be seen as something derived from KL divergence and cross entropy as well. Okay, I also have a video about this, and if you would like, you can check out the video here, which I also list in the description. So I don't want to spend too much time discussing how IDF is an application of KL divergence of that information theory. But based on KL divergence or cross entropy, on the theoretical level, there are a couple of issues that I saw in IDF application in the information retrieval context. And the first one being there's no upper bound in the theory, in the measurement of information. Okay, so let me give you an example. Because we talk about information retrieval, so let's use Google to search for something. And for example, if you search for misunderestimate a person, a thing, or misunderestimate a player, a dog, a cat, or whatever, right? So misunderestimate is a very rare term. And so when you search a combination of things, with a rare term in it, this rare term is actually going to dominate the equation. Okay, so whether you search for misunderestimate a thing, a player, a person, the result will be similar. Okay, and so why is this? The issue is because in IDF, in inverse, because inverse document frequency is a very common method in term weighting to determine the scoring of a web page or a document, right? So let's say, okay, misunderestimate is a very rare term that only appears in 100 documents on the web, which has, let's say, 1 trillion documents total. Okay, so according to IDF, out of 1 trillion, if the term only appears in 100 documents, the IDF weight is going to be something like this. Okay, and if you run this, you're going to get something like 33. Okay, so this is a score. But let's also look at the score of IDF score of the other terms, such as A. Okay, because you are searching for misunderestimate A thing. So what is the weight for A? Let's say A appears in 99.9% of documents on the web. And it turns out the weight will be very small, which makes sense, right? Because it's a common term and it doesn't give you lots of information. It's 0.001. But if you also look at the weight, the score for thing or person, and again, let's assume that maybe a thing appears in 10% of documents on the web. And so it will turn out that the score for thing will be about 3. Okay, so if you compare 3, the score of thing, to the score for misunderestimate, okay, which is 33, there's a 10-time difference. And because of this huge difference, the term misunderestimate will basically dominate the scoring function and render other terms useless. So it doesn't matter whether you enter a person, a thing, a player, a dog, a cat, the result will remain similar. Okay, now this is not yet, this is actually not extreme, because sometimes if you have a misspelling, or if you have a really unique term, such as so with 10 O's, okay, that can be even more rare. And so that score will become greater. And so theoretically speaking, because of IDF being an application of KL divergence, the score can actually become infinite. And think about when you have a infinite value or a huge value in there, the other values, they just don't matter, right? And so in that case, we have a problem, because when people put into the search box multiple keywords, they assume all the keywords will have some contribution to the search result, when in fact, if you have a rare term, the only rare term will be the factor, be the only factor in the scoring function. So this is one problem, because of the theoretical no upper bound of that information theory. Okay, so this is first problem. The second problem, or the second observation that I have regarding the theory, okay, of KL divergence or cross entropy in IDF is that it's even more fundamental. Is this kind of mismatch of certain assumptions against the basic properties of the theory. So let me talk about this. IDF is often used as part of a vector space representation of text data. Okay, so for anyone who have done any text analysis, you know, right? TFxIDF and vector space representation, right? This is probably, if you are new to it, this is probably only the first thing that you are going to also start with. But when you think of a vector space representation, which is a high dimensional space, And that space is actually a Euclidean space. And that's our intuition and also our basic assumption. And in this Euclidean space, whether you measure things, in terms of Euclidean distance, which is a metric distance, or cosine similarity, which is also a function that can be easily and linearly converted into a metric distance function, we assume these measurements are metric distance functions, okay? And lots of algorithms, whether algorithms such as k-nearest neighbors for clustering, or hierarchical clustering, or certain path-finding algorithms, they assume these similarity or distance functions to be a metric distance function because they align with our intuition about the metric space and metric distance in the Euclidean space. Okay, so one key important property of a metric distance is this notion of triangular inequality. Okay, so let me use this as an example. So shown here is a triangle, right? And so on this triangle, there are 3 points, right? But we can think of these 3 points as 3 documents, right? It can be 3 web pages, right? If this is an application for text mining or information retrieval, right? These 3 points are actually real documents represented by the terms or words. And so let's say you want to perform clustering or you want to perform information retrieval. One important function is to measure how close the documents are to each other or how close a document is to a query or whatever. But regardless, right, a way to measure them is to use, for example, Euclidean distance. And so when you do that, if D1, the distance between D1 and D3 is X, and then distance between D2 and D3 is Y, and then the D1, the distance between D1 and D2 is Z, then with triangular inequality, we can always assume that 2 sides, the addition of the sum of 2 sides will be greater than the third, okay? And so this is a very important assumption because it actually affects how algorithms will actually work. Just to give you an example, so if we perform grouping and clustering, and it turns out that perhaps D2 is close to D1 and D3 is close to D1 as well. In this case, because of this triangular inequality, we can safely assume that D2 and D3 are close as well because of this property of metric distance. Okay, but if something is not a metric distance and we continue to hold the assumption and we continue to use algorithms such as k-nearest neighbors or hierarchical clustering, we suddenly have a problem because these assumptions are no longer true. Okay, and so which is the case of KL divergence and IDF, because neither KL divergence nor cross entropy nor IDF as an application of these is a metric distance. And so there's no such thing as 2 sides. The addition of 2 sides is greater than the third. Okay, and so these assumptions will be violated. And so when you try to apply related algorithms based on TFxIDF, okay, in the text mining, in the information retrieval context, we have to re-examine these assumptions and see, how they will impact our computing and analysis. Okay, so this is kind of the second problem that I saw in IDF as an application of the information theory. And so that motivated me to kind of to find alternatives to the existing theory, even though TFIDF, BM25, all these methods have shown superior results in experiments. It was not satisfying, with these theoretical problems, and so the DLITE theory actually took me a number of years to develop, and in the end, it actually captures all these beautiful and important properties that I have discussed. So DLITE has an upper bound. Okay, so it's always between 0 and 1. So it's normalized value. Okay, first of all, and then second, most important part of it is that it also satisfies properties of a metric distance, and so it meets triangular inequality. And so in applications where we have these assumptions, DLITE can also be used, okay, without problems. Now, so these are all about the theory, but it's also very important to say that DLITE also shows great results in experiments, in real world applications. So TFIDF and BM25 have been the default scoring function, in information retrieval, in text mining, and they also had great competitive results over the last 50 years or so, almost half a century. But when I started to conduct experiments on DLITE, it actually showed much even better performance compared to TFIDF and BM25, and the performance, DLITE not only outperformed TFIDF and BM25 on one data set, but actually many different benchmark data sets in information retrieval and text mining. And so on the theoretical level, it was great. Okay, it has all these beautiful properties that are desirable. On the empirical level, right, in actual experiments, it also show great results. And so this is kind of a few things I really wanted to highlight in about DLITE, the discounted least information theory of entropy. Now, there are still a broad range of applications we are yet to test this theory in. And so I'm interested, and I certainly encourage people in the audience, if you are interested in testing this method, I'm happy to kind of communicate, and if you have questions, feel free to reach out. And so certainly right now, as you know, there are lots of development in AI, in deep learning, in the transformer architecture, in the training of such AI frameworks. And so loss functions such as the cross entropy, so a potential alternative is DLITE as well. So I would be excited to see some of the applications there in terms of how this new theory can perform on AI training. Okay, so anyway, this is just I meant this to be a brief video about some highlights, inspiration and intuition behind the DLITE theory, and I hope to talk more about it in future videos. So we'll see you next time.